sharp in 1 hour. So please, Fabian, go ahead.
Okay, great. And of course, I'll be at the Q&A though. I will try to, 1 second, I'll try to monitor the chat a little bit. There was a question on what it means of a mode entering the horizon. Let's discuss that in the Q&A, I would say, because it's a little bit off topic. So, okay, so just a recap of where we ended yesterday, right? We did, yesterday we did perturbation theory based on the fluid equation, so the continuity and Euler equation without pressure. And then we also included the effect of not actually having fluid, namely the fact that we derived the fluid equations by taking moments of the collisionless Boltzmann equation. And so we incorporated the effect of the second moment by adding a counter term. And that led us in the end to this effective field theory of large-scale structure. Let me just make my cursor a little bit bigger. Right. And we also saw that in the same way, we can take into account the leading effect of non-gravitational forces of baryons, right, of pressure forces. So that was neat. So we had a single free coefficient that captures both of these effects. Now, I wanted to spend a few minutes on introducing an alternative approach to perturbation theory, which we call the Lagrangian approach. So instead of So far, we've been working with what in hydrodynamics we call Eulerian fields, right? The density is defined at a fixed spatial position x and fixed time, and the velocity similarly at fixed position x and time. An alternative is to follow the fluid elements, or more accurately, the mass elements, along their trajectory, and labeling each trajectory with a coordinate. And we call that coordinate q. And so why can we do this? So recall that dark matter is cold, right? So it has vanishing initial velocities. So that means initially in phase space, dark matter was on a slice with, everywhere at every position x, velocity 0, right? So just the horizontal infinitely narrow sheet here along the x-axis. So I'm plotting here phase space in 1 dimension, so x and vx, but you have to imagine this really being 3 dimensions, right? So a total of 6 dimensions. Right, and so due to phase space conservation, this fact that dark matter is on this now slice or sheet of phase space remains. So once you start gravitational evolution, then velocities will become non-zero due to gravity and stuff will start to move, but it will remain on this kind of sheet that I sketched here, okay? So in the full space, you have to think of it as a 3-dimensional sheet in 6-dimensional phase space, right? Because at each, this initial condition I wrote in the first lecture is another way of saying that, right? So at a given position x, there's only one discrete velocity where the distribution function is non-zero, right? It's not an actual distribution, it's basically a Dirac delta on that single velocity, at least in this regime and at early times. Okay, so now what we do is we can label each point of this sheet with its spatial position q, and because all particles at that position have the same velocity, initially 0 and then later non-zero due to gravity, I don't need to follow several trajectories from a given point. I just need to follow that one because all of the particles have the same velocity. And so forget about this gray region that will become later. Just think of this black line as denoting how a given mass element moves in the large scale, or not just large scale, in general due to gravity, right? So now we want to follow that. So we can write the time-dependent position of this mass element as the initial position plus a displacement s, right? And of course, this displacement by definition, it vanishes at the initial condition. And then to follow this, we just use the geodesic equation, right? Those are perfectly valid for this mass element, and it's non-relativistic, so they obtain the simple form that we already derived in the first lecture. Good. Right. So then if you plug that in, this ansatz into these equations and combine, that's actually, I think, one of the homework problems. You get this equation for the displacement, right? So it's at fixed q, it's just an ordinary differential equation for s, for the displacement, so for the trajectory. The only complication is that we need the gravitational potential along the trajectory, of course, right? So when the particle's here, it will continue to move according to the gradient of the gravitational potential here, and similarly here, right? So we need to actually take the gradient of this potential at the fluid position, x fluid, right? The gravitational potential is still well defined only as a function of spatial position. It's part of the metric. Okay, so how do we go forward? So we obviously need to determine this potential still, right? For that, we use the Poisson equation, and the Poisson equation relates potential and density. So we need to compute the density, right? And there's a neat trick how we can do this, because if we know one thing, then we know that mass is conserved, right? The number of dark matter particles or baryon particles doesn't change. So we can use mass conservation and just equate the Lagrangian density rho d3q to the Eulerian density d3x, right? That's number conservation. And what is the density in Q space? Well, I'm using co-moving coordinates. So it turns out that this is, first of all, we think of Q as the initial position. And at the initial time, there were no density perturbations, right? They were vanishingly small. So I can treat this as being at the background density. And because I'm dealing with co-moving coordinates, here, this a cubed factor that you get from the evolution of the background density just drops out. And we obtain this relation. So rho bar d3q is the actual perturbed density times d3x. So I take the ratio, and that is 1 plus my desired density perturbation. And that's the Jacobian of dq over dx, the inverse of dx over dq. And so I can write it in terms of the derivatives of the displacement itself, right? So that's very neat. So I can actually phrase everything consistently in terms of the displacement. And then the idea is to solve this, again, order by order. So we write the displacement as a linear displacement in second order, and so on, the same way as we did for the density. And we can actually show that if you expand everything consistently, then perturbation theory in this Lagrangian approach and in this Eulerian approach using the Euler and continuity equations, that they agree exactly, right? So this is just a different coordinate choice, right? So as long as you're in the perturbative regime, they agree. It's just a coordinate choice. What is interesting, though, is that once you go beyond perturbation theory, then interesting things happen. Whereas a fluid, of course, a fluid has a well-defined density, well-defined velocity at any given point, right? That's the degrees of freedom that we write down. But here, if you look at this equation, right, you can imagine a case where two particles, two mass elements, starting at different positions, happen to end up at the same final Eulerian position, x, right? There's nothing in these equations that prevents that. And this effect, which is physically there in the real universe, is called shell crossing. And it is possible because dark matter is collisionless, right? And we approximate baryons as collisionless also. But in any case, dark matter is collisionless. And so this is perfectly valid. You can have two mass elements that just cross through each other and just are at the same point at some instance in time. This cannot happen in the fluid picture, of course, because, as I mentioned, there's only a well-defined, I mean, what would the velocity be here, right? We have two, it's multi-values, so it doesn't make sense. So this cannot happen in the fluid picture. It can happen in the Lagrangian approach. So in this sense, this approach is closer to the correct physics and closer to what simulations are doing. Good. I see no questions in the chat, so I'm going to continue.
There's one hand up. I'm not sure if if Moro Were want to ask a question.
Yes, please.
Okay, maybe not.
Can I ask a question?
Yes.
So this is really only due to the nature of the particle, has nothing to do with the space itself, right?
Yeah, so I mean, this is, you can still think of space-time. These are not black holes or anything. This is space-time is very smooth, still a smooth gravitational potential, but because particles, non-interacting particles, can just pass through each other, basically. I mean, in the end, there is, of course, they don't pass exactly through each other, but we're always considering some coarse-grained view, and in that coarse-grained view, they're like two clouds of particles moving through each other. Does that answer the question?
Yes, thank you.
Good. So let's continue this phase space view a little more, right? So I argued that initially dark matter lives on a thin sheet, and that sheet remains a thin sheet. And now consider an overdense region that collapses, right? For simplicity, just let's consider it as spherical. So if I'm at this point, right, I'm at some negative x position. So I'm here, and there's an infalling velocity, so along the positive x-axis, right? So the velocity will look like this here. And at the center, there's no velocity because it's just at the center of the spherical mass, so it goes through 0 here. And on the other side, I have the opposite. So so the phase space sheet is doing something like this, right? Very roughly. Okay, if I consider this one-dimensional cut here. Okay. And then if I cut the phase space distribution at one x slice, of course, if I'm in this regime, there's only a single valued velocity, right? So this is something I can perfectly well describe with a fluid, right? At each point in x, there's a well-defined unique velocity. But now let me continue the collapse. And eventually the inner parts of the matter that forms this overdense region will have actually gone through the center and back out, right? And it will meet materia from the outside that is still falling in, right? So I will have a point where two shells of mass cross each other, right? But in opposite direction. It's basically what I described a few slides earlier. And so at this point here now, I will have one shell that is, for example, close to 0 velocity because it's about to turn around and fall back in, and the other that is still infalling and has positive velocity. And here's an example of now how this phase space sheet will look. Okay, so keep in mind, phase space conservation implies that the sheet always remains intact, right? It doesn't get destroyed or smoothed out. It's always a thin sheet, but it starts to wrap around itself, right? So the sine curve becomes bigger and bigger, steeper and steeper, and then it starts to wrap it around itself as the shells move in and out and start to cross each other. And so, for example, if I look at the point fairly close to the center here, I will have streams, we call them streams, of with different velocities. So 1, 2, 3, 4, 5 streams of different velocities, right? So that is clearly a regime I cannot hope to describe with a fluid picture, right? So for that, I need, well, in the end, I need to go back to the collisionless Boltzmann equation to solve this. And okay, that is the end of this lecture. So let me move on to the next one. Good. Okay, so now we dealt with perturbation theory. Now we're here in the simulation section, right? Good. Notation unchanged. One thing I wanted to add, because we had a question yesterday on the linear power spectrum that was an excellent question, and I think we have a bit of a gap here. So let me just introduce how we get to the linear power spectrum again. So we start with the scale invariant power spectrum of curvature perturbations generated from inflation that Valerie will introduce, I think today, I'm not sure, which is basically k to the minus 3 with some small correction. And then we use the Poisson equation, which I just reformulated here using, it's just plugging in omega m. So it's basically the same. It is the same Poisson equation we considered earlier. And now I need to relate phi, the gravitational potential, or psi, it doesn't matter in logical structure, to the curvature perturbation. And that is given by this relation. And this relation, I think, we probably haven't shown it to you. And that's, of course, a very important relation. So what does it contain? So the perturbations and the potential are proportional to the curvature perturbations, but there is this transfer function factor in between, which encodes how the perturbations evolved in the early universe as they entered the horizon and then underwent the transition from radiation domination to matter domination. All these early universe effects are encoded here. And then we have the growth factor that we studied in detail in lecture 1, right? There's a factor 1 over a here simply from the Poisson equation. So the final result is this, okay? It's a complicated looking expression, but keep in mind that there's really only 3 ingredients. The primordial power spectrum, which comes out of inflation, the transfer function, which comes out of the early universe, and the growth factor, which we have computed. In particular, power spectrum scales, the only time dependence is growth factor squared, as we showed in lecture 1. Good. Okay, so I hope that closed the gap. So let's go back to structure formation beyond perturbation theory. So we have to go back to the collisionless Boltzmann equation. But for our problem at hand, we will not need to really do the full 6D calculation, right? Which, as I mentioned, is incredibly complicated and difficult. We will actually use the fact that matter always lives on a sheet in phase space, right? So we will only be interested in following this sheet. That's all we need to do, and that's a 3-dimensional sheet. Okay, so it actually makes our life quite a bit easier. So the idea of n-body simulations is to take this sheet in phase space and discretize it, divide it into little patches, and then follow these patches. Okay. And these patches of the phase space sheet or phase space elements, we always call particles because it's just such a nice analogy, right? But it's important to keep in mind that they're not actually dark matter particles, right? They stand for elements of this sheet in phase space. Each element will consist of, huge numbers, whatever, 10 to the 30, 10 to the 50 dark matter particles. And it actually doesn't matter how many particles make up this sheet. We only are interested in that there is such a sheet, right? So this whole idea is totally independent of what the mass of the dark matter particle is, whether it is actually a particle or maybe a field. As long as its phase space distribution is a sheet, we can solve it with this technique, okay? And so the important thing always to remember is these are not actual physical particles. Still, I will call them particles, following the standard lore in our field. So, and then what's the evolution equations of an element of phase space? Well, it's just a geodesic equation, right, as we argued before. So formally, we're integrating the characteristics of the collisionless Boltzmann equation, but it's just the geodesics, which in turn are basically just the Newtonian equations of motion. Right. So these are the equations I gave in, or derived in the, well, I didn't really derive them, I guess, but I argued why they look like this, the geodesic equations, in the first lecture. And so let's do one more transform. We introduced this super co-moving or momentum, or whatever, the name is not important. We just take momentum and multiply it by A, right? And what does it do? Well, to the velocity equation, it just adds a 1 over A. But the nice thing is that it gets rid of this Hubble drag term, the HP term. And so dp c dt is really directly given by the gradient of the potential. Okay, why is this nice? Well, it's nice because this means that in the absence of perturbation, the momentum is actually constant. And that is always good for code evolution purposes if you have a conserved quantity in the absence of perturbations. So this makes it much nicer for the code and actually, improves the mathematical and numerical properties. Hold on. Just open the chat again. Okay. Good. Okay, so this is the equation we have to solve for the phase space elements or particles. And then, of course, we need the potential again, so we need to solve the Poisson equation as well. Okay, so let's begin very simple, and let's just do one step. Okay, I'll just calculate the potential once, compute this once, and then compute the position x up to today. And that's nothing other than the first order treatment of this Lagrangian perturbation theory that I described earlier, where we're solving for the displacement in orders of perturbations, right? So first order Lagrangian perturbation theory, also known as Zeldovich approximation. And so you start with a uniform grid of particles, and you displace each of them according to the potential gradient, and you get this. And so this already kind of looks like structure, right? So it's pretty neat. I mean, it's a really simple calculation, and you can already see that stuff accumulates in these massive structures, and you have these big empty regions connected by filaments. So it's all already there. In practice, of course, we do much more involved calculations, but this technique is useful for generating the initial conditions for the simulations. Okay, so there's two things we need to do for an n-body simulation. One is the integration of the particle trajectories, and the other is the calculation of the potential or the forces. Okay, so let me start with a time integration. So typically, simulation involves some version of what's called the Leapfrog Scheme. So here, basically, the time step is the age of the universe, okay? I start from really zero initial conditions. Take the linear potential gradient and then move the particles all the way to redshift 0 with that. So in this case, it was really just one giant time step from early universe to today. In the actual simulations, we'll of course do hundreds or thousands of time steps. Good. And so these time steps, we do a leapfrog scheme. So that means we have the position and the velocity or momentum at staggered epochs. Okay, so we have the position here and the momentum one half step ahead. Then I can advance the position using that momentum. And then I use the position here to calculate the force, the potential, and then I move the momenta according to the force. And so I go like this. And this is just a very neat trick that it cancels a lot of error terms. So it preserves energy, for example, to cubic order. So basically, the sequence is always the same. You start somewhere in this cycle. Say what I described, we just start by moving the particles. I have x at position t, and I have for each particle, so I indicates the particles here, right? I have the momentum at t plus delta t over 2u, and so I move the particles according to that. Then I use these particle positions to compute the gravitational forces for each particle, and then I move the momentum by a corresponding amount. So I should have probably emphasized a little more the initial condition. So as initial condition of an n-body simulation, I need to start this chain of steps somewhere, right? And that initial condition consists of a set of particle positions and momenta, right? Because dynamically, that's what I need to know to solve the future evolution. And those we can compute, for example, using the Zeldovich approximation, right? So this first order Lagrangian perturbation theory, which I didn't describe in detail, but you can actually do a homework problem on that. And so there's no randomness involved as long as you have a linear density field given, right? Linear density field allows me to compute the linear potential. That allows me to compute the positions and momenta of the particles at linear order, and then I can start my simulation. So there's no randomness involved, but of course, to generate the linear density field, I typically sample from the linear power spectrum. So there's a randomness involved in that step. Good. So this was the time integration. But the second part is, of course, the force integration. So here is now, again, as always with numerical techniques, there's a trade-off between accuracy and computational cost. So back in the days when these types of simulations were first done, typically in the galactic dynamics context, people actually summed up the forces of all particles on any given particle, right? So that is, if I really have, point particles, that is the correct thing to do, right? The gravitational force at position xi is the sum over gm. All particles have the same mass here of xj minus xi over this thing cubed. Now the problem is if I have n particles, then I need to compute this for all n particles, and that scales as n squared. And so our goal will be to run simulations, have billions of particles, okay? So if you have an algorithm that scales as n squared and you have a billion particles, that means 10 to the 18 operations. That is a state-of-the-art computation on the largest supercomputers today. And that's just for one time step, right? For one force calculation. So clearly that doesn't work. So whatever we do, we need to find an algorithm that scales as n, ideally just linearly in the number of particles, or perhaps n log n, that's fine too. And another important point is that we actually don't necessarily want this because this is for point particles. And again, our particles are really elements of the phase space sheet. So it doesn't actually make a lot of sense to treat them as point particles on very small scales. Yeah, so simulations are typically around 1,000 megaparsec, 1 gigaparsec on the side, and upwards of that for cosmological purposes. For galaxy purposes, people go down to 100 megaparsec on the side. Good. So, okay. So how do we go beyond this direct summation? So the first thing one can do, and that's the first thing if you're taking a class like I did during grad school where your homework problem is to write an n-body code, then they will probably assign you to follow this algorithm because it's the simplest. So here the idea is, instead of, we just put the potential on a grid and solve the Poisson equation there. Okay, so if you have a collection of particles, you can assign a density field by just distributing the mass of the particle on the grid. So one example that's illustrated here is you distribute the fraction of the area of this gray square that is contained in this square to this cell, and the fraction to this cell and to here. So it's basically a smoother interpolation than just assigning all of the mass to the cell where the particle lives in. And that's called cloud and cell assignment. Okay, so you do that, you have now the density on a grid. So now you can solve the Poisson equation, which is here, using the fast Fourier transform. Right, so you go to Fourier space, multiply or divide by k squared to solve for psi. That's it. And then you go back. And then you interpolate. So then you have the potential on the grid, and then you can interpolate the gradient of the potential. And the nice thing about this is that it really does scale only as n log n in the number of grid cells and particles because of the fast Fourier transform. So, I mean, the fast Fourier transform is a beautiful, amazing algorithm. So I really encourage you to read up on how that works. It's really beautiful. Good. So now what is, of course, this has a downside, right? The downside is now that whatever I do, my force resolution is limited to the size of this grid, right? I cannot resolve anything within the grid cell. So doing something like I showed here, the Millennium simulation, where I can zoom in and see all this beautiful structure, no way can you do it with this way, because you would need an enormous resolution. And even though the computational cost scales as n log n, if you want to increase the resolution, you have to pay a price of n cubed, right? So increase the resolution by a factor of 2 means 8 times more grid cells, means 8 times more memory, and 8 times log 8 more computational time. So that is a big downside. Indeed, we wouldn't make much progress if we just had that. But fortunately, we actually don't need that high resolution in a large part of the volume, right? So a large part of the simulation volume is actually fairly smooth, and we don't need a high resolution there. So the idea to deal with that is to use adaptive algorithms, which only increase the resolution where it's necessary. And perhaps the most obvious way to do that is what's called adaptive mesh refinement. So imagine you have this collection of particles shown as these gray dots. So in the uniform regular grid case, you would only have this red base grid, for example, right? 4 cells, let's say. So now you couldn't really resolve what's happening in this cell at all, because you just have one cell and a bunch of particles in it. So adaptive mesh refinement works by splitting any cell that crosses a certain number of particles into 8 subcells. Okay, so here is a 2D representation. So it's, I'm always splitting into 4 subcells, but you get the idea, right? So in 3D, it will be 8 subcells. And so you repeat that iteratively until every cell is below the density threshold. And so that's conceptually straightforward extension of the grid technique. And the nice thing is you still have a grid. You can use that same grid to do, for example, hydrodynamics. Right. So basically when you run a simulation, you ask yourself the question of, so answering Nico's question, you ask yourself the question, how much volume do I need? That's given by how much statistical precision you need, and then how much resolution you need. And that basically sets the requirements of how big your grid size has to be, and then if you're using adaptive refining code, how much refinement you'll have to use.
May I just
Yeah,
ask?
so, yes?
Yeah, but you don't want to go to a really lower scales. Like you don't care about individual stars or anything in that sense,
Yeah,
right?
so there's always a fundamental resolution limit, yes.
Exactly. Okay,
So
thank
in
you.
this case, for this adaptive mesh refinement, basically there's naturally, by the number of particles you have, there's kind of a limit, right? But you typically also set a floor on the refinement levels. But in the end, in these adaptive simulations, what sets the final resolution is really the number of particles you have, right? Because in the end, if you have one giant particle that comprises basically 10 to the 8 solar masses of stuff, that will not form stars, right? It's too big to form individual stars. So there is a limit to what structure you can reach just by the number of particles you have. Yeah, so finishing up with the AMR, adaptive mesh refinement. Yeah, so conceptually easy. In practice, it's unfortunately a bit cumbersome because if you look at solving the Poisson equation here and this subgrid, right, you need to put in the correct boundary conditions that matches the coarser cells on the boundary. And for that, to match general boundary conditions, you cannot use FFT techniques, and you have to use relaxation. So it gets a little more costly. The other algorithm is actually get rid of the grid. Couldn't help myself there, that pun. So you basically directly try to sum particle forces by lumping particles together that are distant to a given particle, right? So consider this 1D representation here. Black dots are particles again, sorry, gray dots. So from the point of view of these particles, the fact that these 3 particles are actually 3 distinct particles and not just one bigger massive particle is totally irrelevant, right? That these things, basically, these 3 particles look like a point mass to this particle. And actually, this is probably even true for these other particles. So I can lump all of them together into this structure, right? And so the idea is to do a multipole expansion of the gravitational potential and only retain the lowest multipoles for particles that are far away. And the distance hierarchy between particles you do by constructing this hierarchical tree. Okay, so particles are grouped to parents according to how close they are. So for example, if so lambda denotes the center of mass of some group of particles, right? So if I sum over individual particles, I'm summing over this term, and that at lowest order, if the particle is close to the center of mass, much closer than the distance, then this is basically, I can treat the whole thing as one particle, and this gives rise to the monopole term. And then the leading correction would be this dipolar-like term. Yes, dipolar-like in the potential. So then, so basically, then you have to decide. So for adaptive mesh refinement, there was this criterion of maximum number of particles per cell. Now there's a criterion of when do we keep this dipole term, for example. And if you look at the relative size of this guy to this guy, it basically corresponds to the apparent angle that these 2 particles subtend from the point of view of a distant particle. Okay. So basically, we define an angle and say that particles that appear within an apparent angle, that we group them together, and we don't need to consider dipolar-like forces. Okay, so that's how this tree algorithm works. The advantage is that I think it's a very elegant method. You don't need a grid. You don't need relaxation. The disadvantage is that in the end, we are simulating cosmological volume. So in the end, we want periodic boundary conditions for the whole volume, right? Because we're not simulating a box in empty space, we're simulating a box inside the surrounding universe. So it's hard to put in periodic boundaries in the tree. So what people do instead typically is to add a grid at the base level, and then you need to split forces into grid and tree forces, and that's has its own little issues. Great, so that was my brief tour of algorithms for cosmological simulations. I wanted to talk a little bit about the history because it's kind of neat. So the first actual NBOD simulation was run by Eric Holmberg, and he did not use computers. Instead, he used light bulbs and used the fact that the gravitational force scales as 1 over r squared, right, from a distant particle, but the light flux from a distant light source also scales as 1 over r squared. So he placed an array of light bulbs, and each light bulb also had a photodiode, and so he could measure the flux from the surrounding light bulbs and then determine which direction this light bulb had to move. Okay, so this is a kind of neat technique. It doesn't work with billions of light bulbs, of course. I mean, we don't have that many, and I think he actually only simulated planar geometries because it's also hard to move light bulbs in 3 dimensions. But that was the first n-body simulation. And then soon enough, of course, people started using computers for this, starting with a few hundred particles for galactic dynamics. Then in the 80s were the first properly cosmological simulations by Davis et al., which actually they ran a suite of simulations for different cosmologies to rule out which cosmologies could describe our universe. For example, hot dark matter could clearly not describe the observed structure in the universe because it was so off in terms of the distribution of collapsed objects. So really the whole program of, studying large-scale structure formation in detail and comparing with observations to get cosmology, that was started with these types of simulations. And then today we're in the regime of, I think this one is one of the biggest in terms of volume. It has multiple gigaparsecs on the side. This was run for the Euclid survey. So we've truly come, I think, of order 10 orders of magnitude or 9 orders of magnitude in terms of particle number and resolution. Quite impressive. Good. So now finally, let's look at the results of this n-body simulation, right? So in the end, what we get is a catalog of these particle positions and velocities at various points in time, right? We can have the code give us an output of the particle positions and velocities anytime we want. And really, again, right, we're following this phase space sheet, so we're really having the position of the phase space sheet after gravitational evolution. And apart from this resolution limits I described, that's really pretty much accurate, right? So they really simulate a collisionless Boltzmann equation accurately if the initial conditions are cold, right? Right. Yeah, I'll get to that question in a second. So yeah, so this plot again shows a slice through the density field in logarithmic units through an n-body simulation, and the different panels are zooming in. Okay. And this is now a video of structure actually forming. So you can see it starts with a fairly low density gradient, and then the structure continues to sharpen in the overdense regions, and then these large underdense regions begin to appear, and the density contrast keeps growing, and the structure keeps condensing into more and more massive and compact structures. Yeah, and so the reason it looks, again, keep in mind that these are co-moving units, right? So the whole thing is expanding as this video happens, right? And we're just considering coordinates that move with the expansion. So the stuff that is actually, seems to rapidly collapse is in fact not collapsing as fast because it's taking out the expansion factor. And that's why things don't seem to be moving so much because we're using co-moving coordinates. Good, and I think I had another video. So this is now, again, that slice to the Millennium simulation, and now we're zooming in at fixed time, okay? So this other thing was a video of the dynamical evolution, and now we're moving in, and you can see really these different types of structure, large underdense regions, filaments connecting them, and then basically compact structures at the centers of these filaments, and you keep thinking, okay, now we got it, but you can, because this enormous dynamical range with the tree algorithm that you can get, or with adaptive refining algorithms, we can keep zooming in and zooming in into these finer and finer resolved structures. So, yes. And there was a question, how n-body results can be compared with observations. So first of all, yes, so we can get a power spectrum. For example, this is the density field, right? We can compute the power spectrum of the density field. And on large scales, at low k, it will agree with linear theory. And at higher k, it will depart. It will show strong nonlinear effects. And then we can actually compare perturbation theory and see how far perturbation theory is valid. That's one example of how we can use n-body simulations. Right. So yes. So I already mentioned these different types of structures. So the 3D, I mean, you can kind of classify them topologically as the 3D dimensional underdense regions, which we call voids. The 2-dimensional sheets, which are not really very visible, they're not super distinct. We also called pancakes. The 1D filaments, which are, of course, quite clearly visible. And then finally, the bound structures, halos. So in cosmology, typically, we're most interested in these voids and in these halos. Why? So the halos I will talk a lot about because halos are really the hosts of galaxies. So by studying halos, we can kind of get an idea of what galaxies, how galaxies are distributed in the structure. Voids are interesting because they're obviously underdense, so they're less evolved. It's easier to build theoretical descriptions for them, and so they have gained some interest as a cosmological probe. Good. So let me talk a bit more about dark matter halos then. So dark matter halos are defined as bound structures of this simulated matter. And recall that in these simulations, we're always simulating both cold dark matter and baryons, but we're just neglecting the effects of baryonic pressure and so on, right? So they're really, some people call them dark matter-only simulations. I think that's incorrect. It's accurate to say these are gravity-only simulations. So then basically there's well-defined objects or bound objects inside these inside this huge volume, right? And they're also the densest regions, okay? So matter never gets any more dense from a cosmologist's point of view than in halos. And the relevance really is that that we believe all galaxies to be hosted by a dark matter halo of some mass, okay? And for this, we actually have evidence. So if you look at the dynamics within galaxies or of galaxies and galaxy groups, or if you look at gravitational lensing around galaxies, then you find that there's much more matter than the visible baryons, and that this additional matter is much more extended than the baryons, right? And that's where this term halo comes from, because you can think of small galaxies sitting inside this much bigger structure of dark matter. And so as you go to the most massive halos that exist in the universe, those are actually associated with whole assemblies of galaxies. So that's why halos are highly relevant to observations, but it's not easy to directly link them, right? Because we don't see the dark matter. So most studies of halos are basically in simulations. Good. There were some excellent questions here about the tree. Please ask that again in the Q&A if you can. Right. So I have a few more minutes. So let's see. Yeah, let me just run through this quickly so that this topic is concluded, and then let's see if there's time for questions. Okay, so how do we find these dark matter halos? There are codes that are specifically designed for this. They're called halo finders. Basically, you start from the maxima in the density field, and you determine which particles are bound to this structure iteratively, right? So you can compute the relative velocity between the particle and the center of mass of the halo, and you can compare that to the local escape velocity, and you can determine whether they're bound. One of the issues we have is how to define halo mass. You might say, well, why don't we just really count all bound particles? The problem is that this is, first of all, affected by numerical noise. So if you change the simulation, this will change. And it's also not practically relevant in the sense that we don't really observe dark matter. So, so instead, what we usually do is we say the halo's mass is defined by the mass contained within some radius, some spherical radius. So some spherical radius, region of some radius, and then we need to define that radius. Unfortunately, there's no well-defined definition because the halo kind of smoothly extends to the surrounding structure. So typically, people use a criterion of some number, say 200 times the mean density. Right, so then the halo's mass is all the particles that are inside a radius that encloses 200 times the mean density. So a special case is when you choose this delta equals 1. Okay, so we call that the Lagrangian radius. So that is actually a physically well-defined scale because it's the typical size of the region in the initial conditions that the particles that make up the halo today come from. Right, so that is actually an important scale, and we'll use that later. So then you can plot, once you've decided on a definition of halo mass and on a halo finder, you can plot the distribution of halos as a function of mass. You find that low mass halos are much, much more numerous, and they kind of follow a power law distribution up until the highest masses where there's an exponential cutoff. Okay, so this is phenomenologically what we find, and we understand where that cutoff comes from. Then the interior structure of halos. So halos are not smooth, but what you can do, of course, is you just compute the spherically average density profile. And that's what Navarro, Frank, and White did in 1996. And they found that all halos, regardless of the mass, even changing the cosmology of the simulation, they all have this universal form with a power law index of -1 close to the center, -3 further out. This is the NFW profile form. It's still a bit of a mystery where this universal profile comes from, right? Because halos form with vastly different history. Some of them just slowly continuously accumulate matter. Others formed out of massive mergers of two almost equal size objects, and yet they still, in the end, all have the same profile. So it's a bit surprising, and we don't really know why that is. So it's just an empirically found fact in simulations. But then, again, so in practice, halos are not smooth, right? They show all this graininess, the substructure, and the relevance for us of this substructure is that it will host galaxies, right? So we believe that galaxies form inside this substructure. And so the substructure is really smaller halos, much smaller halos that formed at earlier times. Remember that structure forms first on small scales and then assembles to larger scales. So these small scale halos formed first and then later assembled to bigger halos. But because they're dense, their cores are dense, they remained intact, right? So a bigger halo is just a coagulation of smaller previously formed halos with some smooth component added in. Right, so of course that is all good and well, beautiful pictures, beautiful things to study, but we, in the end, really want to see what galaxies do, right? So, and that will be the topic of the fourth lecture. Okay. Are there any in-person questions? Or should I go through the chat? So there's a question of have all halos shown this shell crossing and the wrapped mass sheet? Yes, they have. So basically, in order for a particle to be solidly bound, it has to at least go through, say there's a halo here, it has to go in, come back out, and then come back in at least once for us to be able to, for it to lose enough kinetic energy dynamically to stay bound. So basically, all the bound particles have it wrapped at least one time. So the timescales, you cannot. No, we can simulate earlier times. So the timescale of halo formation is basically, it corresponds to the dynamical time of the object you're looking at, right? And so if you have a small dense region, the dynamical time of that is short, and that thing will form earlier than a larger region. So small halos form first simply for the reason that I mentioned in the first lecture, that the amplitude of density fluctuation is highest on small scales. So one more question I see is, do we need to calculate a truncated multipole expansion for each particle, and how expensive is this? So basically, the idea is, oops, that was my fault. So the idea is that you only, when you have a particle that you, so the problem is now that I have multiple, I think it's this one. Right, so the idea of tree is that if I say, all of these particles, all these gray points here are below my opening angle, right? Then I need to only know the position of the center of mass, which is stored in the parent particle, right? So the parent particle, meta particle labeled here, stores the center of mass of all the constituent particles. So I only need the center of mass to compute the force, right? So I don't have to deal with any of these particles. So in general, you can also have this thing store the higher multiple moments of the distribution, and then basically at each point when you construct the tree, you have to compute not just the center of mass, but also the higher multiple moments, and then you can evaluate the higher order expansion of this. So I'm not an expert on the tree algorithm myself, but I hope that answers the question. Yeah, so the question, can an AI run this more efficiently than an n-body simulation? Perhaps. People have worked on this. The thing is, though, that you would never trust the AI away from the region where it was trained, right? So, so that means in the end, you still need to be able to run full n-body simulations in order to test your AI, right? That is, I think, one of the issues. And I don't know. I mean, n log n is a pretty good scaling. I don't know. It will be hard to beat, I think. But so I think I need to, unfortunately, leave. But if there are more questions, I'm happy to take them tonight at the Q&A.
Okay,
possible.
So let's thank again Fabian for the lecture. Yes, and remind us, he said that there's a Q&A. So there's some other questions. There was Riquelme, I think, had his hands up. Of course, you can ask questions in the Q&A.
And in the chat, and also in the Slack, right? I'm also looking at the Slack.
That's right. And we meet in approximately half an hour for the inflation lecture by Valerie Donke. So see you guys later.
Bye.
Thank you. Bye-bye.